Welcome back. In this problem, I'm going to look at sinusoidal steady state analysis, and we will do that with phasors. It's a lot easier to play with phasors and algebra than do differential equations and worry about trigonometric relationships with sines and cosines to try to follow that analysis around. And what we've learned then is to wait for our system to reach a steady state or to have the transients die out, and then what we're left with is only sinusoidal signals moving around in the circuit. And in this particular problem we actually have two sources, a current source and a voltage source. The observation to make here is that both of those sources are oscillating at the same frequency, and so we can actually treat them together and not have to worry about breaking them apart. But we could perform this analysis using superposition and treating one source present at a time, and that's the preferred way if those were actually at different frequencies. Then we would actually be looking at two different sets of impedance values for our inductor and capacitor. In this particular case, let's make the following statement formally, and that is to notice I sub s of t and v sub s of t are at the same frequency. And I think it's pretty clear that that frequency for this particular problem is 4, and the units on that frequency are radians per second. Remember, omega is 2 pi f is equal to 2 pi over the period of that waveform if you need to relate hertz or radians per second or period of oscillation in a given problem. If those sources were not at the same frequency, then we would need to treat each source individually, or we would need to solve two separate circuits using the concept of superposition. Since these are linear circuits, that would allow us to solve each one separately and then add the total to obtain our response with the two frequency components in that response. Using superposition, we would then have different complex impedances, or different z sub l's and z sub c's in each of those two circuits. In this particular problem, we don't have to do that because our frequencies are both at 4 radians per second. What we're wanting to do in this problem, and note that R is the same in all three places. R is 1 ohm. The inductance is 1/4 Henry, the capacitance is 1/4 farad. We are wanting to find I sub 0 of t in the sinusoidal steady state, or we're wanting to find, in this particular problem, a sinusoidal steady state expression for I sub 0 of t. Meaning what we're wanting to do, we're looking for something for I sub 0 of t, which will be some magnitude times cosine, and we already know the frequency that that's going to be oscillating at some angle. This is now the solution that we're trying to find. We're trying to identify the magnitude and the angle of that sinusoidal current I sub 0 of t that's flowing through that vertical resistor on the right, and that's after the circuit has reached steady state, which for reasonable values of frequency and inductors and capacitors, it's not going to take very long for the transient to die out. It will be 5 time constants from when we energize the circuit. So what we're wanting to do is we're wanting to find this, and we're working with sinusoidal steady state conditions. Which means that everything in that circuit, all the currents and voltages, will be oscillating at 4 radians per second. They may just be slightly changed in time relative to each other, or there may be a phase shift, and that's what the theta represents. And if we're in sinusoidal steady state, the transients have all decayed or gone away, and we only have sinusoidal signals left for all of our currents and voltages. And those, because our two sources are at 4 radians per second, all of those currents and voltages will all be at 4 radians per second. And that's only have sinusoidal signals at that frequency are in the circuit. To start this, it's easier, as I said, not to worry about the differential equation relationship, which is what's actually going on, but we've now decided we're going to wait for the transients to decay and only do sinusoidal analysis. That allows us to play with algebra and complex numbers instead of differential equations and sines and cosines. If that's what we want, then we're looking for the different phasors and complex impedance that we have with respect to our inductors and capacitors. For the phasors, we have our two sources. We have our current source, which was little I sub s of t. That had a magnitude of 2, and it had an angle of 0 degrees. There was no offset in the argument. It was just 4t. Our voltage likewise did not have an angular offset, and it had an amplitude of 6. So there are our magnitude and phase, or magnitude and angle, for our sources. Our impedances, the resistors do not depend on frequency, and for that reason we don't really worry about their impedance, but all the z sub r's are going to be 1. The impedance of the inductor for sinusoidal steady state is j omega L, omega being the frequency, L being the inductance value or inductor's value, 4 times 1/4, and so the impedance of the inductor for this frequency is simply J. The impedance of the capacitor is 1 over j omega c. That's now 1 over j times 4 times 1/4. And now we have 1 over j, which we can clean that up a little bit if we want to. We can multiply that by 1. And so now we have j over j squared. But j, remember, was the square root of -1 in our notation. Square root of -1 squared is -1, and so we end up with minus j for z sub c, the impedance of our capacitor. We're now in a position to redraw that circuit and start playing with algebra, but with complex numbers. So now we're going to redraw the circuit using complex impedances that we just found and the phasors for our sources. Which leaves us then, or provides us with, the same resistor. Here's an inductor, which now is simply a complex impedance J. Our resistor value is 1. We had our source, current source, going up. It has a phasor description of 2 at 0 degrees, which really we could probably just write that as 2, but we'll go ahead and keep track of the angle. The source voltage was 6. We had another 1 ohm resistor, vertical, and that was actually the branch where our current was that we're trying to solve for. And we also have another resistor and this capacitance of minus J, and the resistor value is 1. We now want to analyze this circuit. And as you're looking at this, you need to be thinking about the different ways that you could maybe analyze this. How? Well, one, as I've already commented on, there are multiple sources. In this case, they're both at the same frequency, and so we can actually use or solve this with both of those sources in place. Or if you wanted to, you could 0 one and leave the other one in place, and vice versa, and end up with 2 circuits whose final answers for those 2 would need to be added together to give you your result that you were after. And that's this concept of superposition. Let's not do that, just to make it maybe a little more difficult or interesting to solve. Suppose that somebody said, well, I see some meshes there, so I'm thinking KVL. If you look a little bit more closely, well, initially you see these 3 meshes, and then you say, wait a minute, we have, if I did that, if I had a mesh here, a mesh here, and a mesh here, I don't know what's going on with this voltage drop up or down because of that current source. And so that's going to give us a little bit of a difference. We aren't going to just have these 3 meshes. We have a current source, which we would then need to account for with a super mesh, since that current source is between meshes. And that current source leading to a super mesh, we would have to then write our constraint equation relating the mesh currents and that particular source current of 2. And if we had labeled this I1, I2, and I3, I think it's clear that this 2 is going in the up direction, and then we could relate that to I1 and I2 as 2 is equal to I2 minus I1. That's the net current flowing up in terms of I1 and I2. That's if we would do mesh analysis. The other option is to do a KCL. And if we look at this in terms of KCL relationships, I'll talk while I'm erasing to get rid of some of this other information that we had down. Hopefully it will start to erase. But we had, in this particular case, it looks like the bottom is a pretty convenient place to have our reference node. And if that's our reference node at the bottom, then we could think about that particular node and this node as being our nodes of interest, and we don't really need to worry about that series combination of resistor and inductor and resistor and capacitor, because we can just add those together, and so those are effectively just one big impedance on that side and this side. The only problem that we might have is the fact that we now have this voltage source in between our two nodes, and we don't know the current that's going to go in that path. But because of that, we can actually simply do a super node and worry about writing our KCL equation with that super node, and then using those node voltages as in our constraint equation to relate those node voltages, or to obtain our second equation in the two unknowns. Let's call this particular node voltage V1, and that's a phasor, and let's call this node voltage V sub 2, plus to minus from top to bottom. And a lot of times you might just see somebody label that V1 and this V2, but what they're really meaning is this polarity as I've indicated in the diagram. Let's now look at writing KCL, or let's do that KCL. In this KCL, we have two nodes. We do have a voltage source between those two nodes, and that means that we do need to worry about a supernode, but that will just give us a constraint equation, one more equation in the two unknowns, V sub 1 and V sub 2. So let's try doing the KCL, and we only have two voltages instead of with the mesh we had three mesh currents. Let's try nodal analysis, since we'll have fewer equations and few unknowns in this particular configuration. And let's write a KCL at the supernode, and I think I highlighted that in maybe a purple color before. If I do that, then let me say that this current I will call I1. This current going down is, we'll just consider that going up from the source, so that's a 2 into the node. We also have I0 going down vertically on the right, and let's call this I sub 2 going out. And those are now our four currents that are leaving that supernode. We have I1, we have 2 coming in, we have I0 going out, and I2 going out. Or KCL at the supernode says that we now have I1 minus the source current. It's coming in, it's not leaving the node, that's why the minus sign, plus we have I0 leaving the node, plus I2 leaving the node. There's our four currents that sum to 0 out of that supernode. We can now rewrite those currents in terms of the unknown voltages, node voltages, V1 and V2. I1 going out to the left was just V1 divided by the impedance in that branch, which was 1 plus J. We have our minus 2, that's a given source value. I0 was V sub 2 divided by 1, which was our R, and then I2 going out to the right also had V2 as its voltage drop, but it had then as an impedance 1 minus J, which was the resistor and the capacitor in series to give us the 1 minus J. That's equal to 0. We can now clean that up a little bit. Suppose that we try to clear fractions by multiplying by a common multiple, which is 1 plus J and 1 minus J. That'll get rid of all of the denominator terms. Doing that then says that we have 1 minus J times V1 minus 2, I'm going to drop the angle, 1 plus j, 1 minus j, plus 1 plus j, 1 minus j times v2, plus 1 plus j times v2, and all of that is equal to 0. Now we have just one equation, and that will clean up rather nicely by the choices of our frequency and capacitor and inductor. This is 1 plus j, 1 minus j. We have real part squared plus imaginary part squared. That's going to simplify to 2, as will this. And we can now say that we have, in terms of an expression, 1 minus j v1. And let me go ahead and put that minus 4 on the other side for now, or let me just go ahead and keep it. 2 times minus 2 times 2 plus, we have 2 v2, and we have 1 plus j v2 equaling 0. There's one equation because of the supernode. That's all we have from writing KCL equations. But I hope that you can see that we need, because of the supernode, that actually implies a constraint equation between a constraint equation involving the unknown variables. And if we write KVL around the appropriate path in our circuit, which the appropriate path, if I can find another color, let me use this light blue. Now I'm going to be coming through that drop or rise. I have a minus V1, then I'm going to go through my source, and then I'm going to come back through V2 and end up at where I started. My KVL equation now says minus V1 as a phasor minus 6 plus V2 is equal to 0. And that's my constraint equation. My KVL then says minus V1 minus 6 at 0 plus V sub 2 equals 0. And really we're looking for I naught, which is the current through that vertical resistor on the right, and that actually had V2 voltage dropped across it. So let's solve for V2 in these two equations, which means let's, with this constraint equation, solve that for V1 and use that V1 relationship in terms of the source and V2 to replace the V1 in this particular equation. Or from this KVL equation, we now have the V1. If I put that on the right, then that gives me V2 minus 6 is what V1 is equal to. Let me now put that into where I just highlighted under the V1 up above, and I now have 1 minus j times V2 minus 6 minus 4 plus, and now I have 2 plus 1 plus j V2 equals 0. And if I do the algebra, let me group all of my coefficients associated with V sub 2. I have 1 minus j, and now let me put in the plus 2 plus 1 plus j. That's V2. And let me move the other pieces to the right hand side. I have a 4 piece, and I have a 6 times the 1 minus j. The complex, or the imaginary component in my coefficient for V2 is canceled, and I'm left then with 4 times V2 bar is equal to 4 plus 6 minus J6, or I now have 4 V2 is equal to 10 minus J6. If I divide that out, then I will end up with V2 is equal to 10 minus J6 over 4, or I have 5 halves minus J 3 halves as far as my V2 bar formula. But if I go back to the circuit, which I won't scroll back to, but I can hopefully recall that the current that we were trying to solve for was that current coming down through that vertical resistor on the right, and that was simply V2 bar over R, where R was equal to 1. And so I naught is actually just V2, or it's this 5 halves minus J 3 halves. That's the rectangular form of my complex phasor current value going through that resistor. If I need to take that back into the time domain, which is helpful to do so that you understand where everything is at, I can now find the magnitude and phase of that. I have the real part squared plus the imaginary part squared, and the square root of that, that's my magnitude of that phasor. And the angle of that phasor is now the inverse tangent of the imaginary piece over the real piece. And if you do that algebra, you'll end up with 2.915 for the magnitude. And if you take the inverse tangent of minus 3/5, you will end up with minus 30.96 degrees, and that's the magnitude phase form or polar form of that phasor, which can instantly be used to write down the sinusoidal steady state output current flowing vertically down in that resistor, which we called I naught T. It has a magnitude of 2.915. It's a cosine waveform at the frequency that we had exciting the circuit, which was 4 radians per second, and it's offset by 31 degrees essentially from both of the sources, and it's behind, it's a negative 30.96 degrees. And that now is our answer for the sinusoidal steady state current.